some of the
I'll
formality?
get started on recording. You already did. Okay.
Yeah. So we'll probably skip some of the formality here. But basically, just first of all, thanks everyone for joining us at the WiCI webinar today. As we have shared like in earlier webinars, we started the WiCI Research Center in part because we were interested with the era wireless living lab project. So therefore, WiCI webinar is one mechanism we hope to have a platform so that we get to hear the great work that's happening in the community and also try to explore ways where we can build communities around some of the core technology areas that's critical for rural broadband industry verticals and so on. Today we do have a very special guest, actually, Professor Zhang. Actually, there are actually he has a long, excellent, kind of list of accomplishments that I will probably skip today. Folks can check online. Maybe just like share a few quick notes. One, I think the first time when I heard about Zhang was I was talking to another colleague, actually, Professor Dapeng Wu at one of the NSF panels, actually. I think Dapeng, for folks who may know him, he was known for his for many work, but one of the well-known work in his research has been the notion of effective bandwidth. That's one of the important results in the research community that care about communication quality of service. And then when I was talking about Dapeng, he was saying basically in his a kind of academic journey, he has actually learned quite a lot from some of the earlier work that Professor Zhang has done in his research. I think probably that some of those work probably in the late 90s, right? Probably to the late 90s, 2000. And some of the there, depending on who you ask, people may have different views about what QoS and how to enable that. I think it's good to see that it looks like this remains to be one area that Professor Zhang is actually still very dedicated for and passionate for. So today we would be able to hear some of the latest, I guess, exciting work from Professor Zhang's group. If you look at the bio on the web, he has been leading quite a few very exciting projects, including NSF size kind of large project, right? It's large project on networking for teleoperation, also USDOT center, right, for connecting and automate transportation. So with that, please, Zhang, take it away.
Hongwei, thank you very much. You can hear me, right?
Yes.
Yeah, thank you for the introduction. Actually, the quality of service QoS was my PhD thesis, and the work we did is too early. So before the internet was become commercialized, then when internet commercialized, everyone care about bandwidth, not QoS. And I realized I should have moved to wireless networks much earlier, because wireless network, we know the quality of service still hugely important because we don't have enough spectrum of bandwidth. So that's like a good segue to what I'm going to talk about. Since we don't really have a lot of time, I'm probably going to skip a lot of things I prepared. I go over very quickly. So kind of my background, I started working the networking actually in the wire network. So in the 1990s, the internet was just kind of started the transition. And at the time, internet was not the only kind of network, right? So there was something else called ATM, and a lot of competing technology. So anyway, so I spent most of my early career on wire networking. I only got into wireless networking in 2019, purely by accident. I'm going to talk about how I got into wireless networking. So I've been working a lot on the wire network, on the backbone routing, on the content distribution system, and did a lot of measurement on the wire network, try to understand what the problem issues. So today, one of the things we can look at, when I got wireless networking, first thing we started is actually do measurement, because that's one kind of our strengths. We want to understand how the system works, what the limitation, what the potential, how we can utilize the network. So the kind of second theme of the kind of talk we're going to talk about is on the autonomous vehicle teleoperation, right? So everyone know what autonomous vehicle is, and it doesn't work all the time. So we're looking at the autonomous vehicle teleoperation as an application of a 5G network. That got me kind of into a lot of interesting problems. So let me just move on to the next slides. So somehow the slides. Right. So I kind of got started on the 5G network. Everyone knows that cellular network today play a dominant role. So I'm going to just skip these slides quickly. Basically, we have many users using the mobile network, the cellular network. In particular, we're going to look at the future application need to also use wireless network. So this is actually what one of the reasons I got interested in the 5G network is kind of getting excited by the many promises that the 5G offers, right? So at the time, before the 5G rollout, 5G is supposedly introducing kind of 3 new kind of service beyond just the so-called enhanced mobile broadband, just connect user to the internet, download data, watch a YouTube video, whatever stuff, but also to support a lot of new use case, industrial use cases, right? Remote monitoring, teleoperation, and remote diagnosis troubleshooting for smart manufacture and smart agriculture, which is of particular interest to Iowa State. So here, just some example of what is a 5G network was designed for to support a diverse application, right? So many applications require high bandwidth, like AR, VR, but many also at the same time also require ultra low latency, right? So 5G was supposedly to provide that kind of service, is ultra reliable, low latency service. So that's kind of partially I got excited. So the reason actually I got into wireless network, the 5G was actually officially rolled out in 2019. So Verizon actually is one of the first operators in the US. In fact, actually among the first in the world actually roll out so-called millimeter wave 5G network in Chicago and Minneapolis. So there's actually a little backstory why they kind of decided Minneapolis one of the 2 cities. That's actually, I was actually the first time I heard about 5G, interesting to some of the 5G. Actually, some folks at Verizon contact me because of 2018, actually, for people interested, pay attention to American football. 2018 actually had the Super Bowl happen in Minneapolis. So Verizon actually interested in doing some kind of demo at the Super Bowl event, say, hey, what do we have some kind of interesting thing they can work with for the 5G demonstration. But that actually never happened. So they roll out the 5G. I think that's probably one of the reasons they were deploying things in Minneapolis, but didn't get time for the Super Bowl. So they roll out 5G service, minimum 5G service around the kind of May 2019. That's what we decided. So, okay, we are one of the only 2 cities, and Chicago is not too far from us either. Let's actually do some measurement to see can 5G millimeter wave network actually support a lot of exciting new applications such as volumetric video streaming, etc. So that's how I actually decided to start to work on 5G network. At the time, I actually know nothing, very minimal about the wireless network, especially 5G. So that's how we're gonna get it started. So our kind of perspective is starting from the measurement, right? So this is where we actually started the measurement study of commercial 5G network. At the time, that's the only one available in the May 2019, but later AT&T and T-Mobile also started to roll out their millimeter wave 5G networks. So we're kind of getting started in mid-May 2019. At the time, actually, our goal basically try to understand what are the challenges, right? So we hear all about the 5G promises. We want to kind of understand, does this actually work for all these new applications? So again, someone who actually coming from more networking, wire network application perspective. So we're interested to understand from the application point of view. For example, looking at video streaming, you use a lot of volume, can millimeter wave give us a better performance, right? So that's kind of partially the goal. We actually started working on 5G network. So at the time, actually, there's not really any tool for us to do 5G measurement. So we had to design our own kind of app running on the phone and also the backend cloud to kind of collect data. So we developed something called Active Tracker to do measurement. Later, we actually acquired a professional tool in 2020, which is developed by Akua called XCal tool, which actually allow us to getting a lot of low-level 5G, low-level information, all the kind of message exchange between UE and base station. So that kind of allow us to gain much deeper insights, able to do cross-layer kind of measurement. Right? So since 2019, we have conducted numerous kind of large and small scale 5G measurement study in multiple US cities. We also have student drive from Minneapolis all the way to Chicago, did a lot of measurement in Chicago, but they also go to cross country all the way to Boston, etc. So we had done many trips, including more recently down to Iowa State to do measurement along the way. So I also sent a student actually spend almost 2 months in Europe to study measure the 5G network. In this case, is the more mid-band, where once Europeans started to kind of roll out their 5G network, they mostly roll out the 5G in the mid-band. So we started the measurement. So here just a kind of list of some of the kind of major measurement campaign we have kind of conducted. In the very beginning, we just do very baseline study. I had a paper published. We started looking at throughput and understand how we can predict throughput. Later, as I mentioned, when the 5G mid-band came about, we started the measurement both in the US and also Europe, and also did a kind of measurement understanding the MIMO, and early started more focused on millimeter wave, later focus on 5G mid-band. So the work basically we have collect probably, I would claim, world's largest academic 5G measurement data set, covering, for example, all 3 major operators of the US, but also several operators in Europe. And that's also, this is actually kind of picture of the student doing kind of measurement and near in Minneapolis, this is student in Europe, some of the around in Europe. Later, we also kind of put in the Starlink measurement. We also conducted multimodal kind of measurement related to our teleoperation, putting camera light up on the vehicle. We are doing measurements. We can also capture the environment information. Right? So if you have channel not good, what is really the reason? So we actually have video and the environment we can actually look at. Right? So this is basically kind of show the major measurement campaign, and also has led to a series of kind of publications. So here I list some of the publications, and I don't mean you to read it, right? So the more importantly, also let us kind of important insight how we should actually enhance or even re-architect 5G or next generation, especially to support a vertical application, because the network exists to support application. So that's basically what we have learned. I may not have as much time. So so just kind of quick summary, essentially some of the lesson we learned, right? So what the 5G really have today, a lot of new capability, mostly coming from so-called the 5G new radio. Right? So most of the gain coming from that 5G new radio actually on top of LTE or 4G, which use the low band, mid band, is adding the millimeter wave. Right? So millimeter wave band, which give us a lot of capacity. Right? So the other kind of innovation 5G is so-called the flexible neuromology. I think most of you guys probably know better than I do in this area, right? So the 5G also has some kind of additional kind of minor kind of innovation, like for example, higher QAM, higher MIMO layer, etc. I mean, there's many other kind of improvement I'm not going to talk about, right? So the other part is the carrier aggregation, which you can use. So here basically I want to contrast to show this is the for 5G downlink, right? So the measurement, for example, you look at millimeter wave, give you up to 4 gigabit per second on the UE side through 5G carrier aggregation, right? So the 5G millimeter wave channel, mid-band channel can be up to 100 megahertz, where LTE, the maximum channel bandwidth is only 20. Mid-band can up to 100, where in the case of millimeter wave, the channel bandwidth can be up to 400, right? So you aggregate multiple 4 such channels, you're going to achieve really huge bandwidth. Where in the case of mid-band, and this is T-Mobile data, in fact, and with carrier aggregation, so here you actually have 4 channels, and channel has a different kind of bandwidth. Partially the US in mid-band, the available spectrum actually are kind of somewhat fragmented, right? So T-Mobile actually had to combine multiple one. You can actually achieve in the peak bandwidth, achieve kind of almost to 2 gigabit, right? So if you see that 5G, indeed, we can getting a lot of bandwidth. Throughput is there, right? But the challenging really is not just the peak bandwidth, right? So this is the kind of one of the lesson we learned about studying millimeter wave and 5G mid-band, right? So even though 5G millimeter wave can achieve really high throughput, the problem is that the channel is really sensitive to many factors, right? So for example, user body improvement. So this is actually from one of the T-Mobile website, right? So if you close the door, the channel is going to fluctuate dramatically, right? So this is actually one of the measurement data we collected when you're driving. You can show this is actually early data we show that 5G channel fluctuate quite a lot, right? Especially when you have really high bandwidth. That fluctuation in the means you have 50 or 100 megabits per second fluctuation. That's actually a huge fluctuation, right? So that's actually causing a lot of problems, especially when you have UE, the user second moving, for example, walking or driving, right? So this is actually pose a serious challenge to application, right? So if the bandwidth fluctuates so much, how does application can adapt to such a bandwidth, right? So we know the traditional network bandwidth, especially even today's Netflix or the video streaming, you actually adapt in a much slower time scale than the 5G channel fluctuation. That's actually caused a lot of problem, right? So that's a kind of, I'm going to skip this slide. So this is basically show you, we actually tried come up with a formal way to quantify this variability at a different time scale, right? So look at the different time scale to quantify how things actually move, right? So what the impact. So this is try to just show you when you have minimum wave versus minimum wave here, and this is the mid band, right? So when you're walking, how the channel throughput fluctuate, and this is causing by the so-called the modulation coding scheme. Your channel fluctuate. You had adaptive modulation coding scheme. So this actually show you what's happening. And I'm going to quickly skip, right? So when you try driving, it's even worse. Right? So that's the kind of problem. So this will show you how that impact the quality of experience from the application, kind of basically the store time versus normalized basically bit rate, right? So you have wave, minimum wave, you may actually having much higher bit rate. You can actually getting much higher quality, for example. But on the other hand, because you fluctuate, you're actually causing a lot of store. So video gonna very glitchy. And that's actually not a good experience for user, right? So those are the kind of problem we are coming from the cross layer, try to understand, given the 5G, what can achieve, what is how that impact the application design. Right? So that's the kind of essentially what we have done. This is just give you one example of the lesson we have learned, right? So there's one of the partially due to the reason, as we have actually seen, the mobile operator today, for example, they are looking at the designing 6G now, and none of them actually willing to work, kind of spend money on millimeter wave, right? So they're actually not interested in getting additional bandwidth in the millimeter wave, even though there is more spectrum there. They actually now focus on so-called FR3, looking at between 7 to 12 gigahertz. Most of the, in the US, many of the spectrum have already been used by other users, right? So this is the part, because how do you getting the trade-off between bandwidth and the performance. So that's a kind of a partially the lesson. Other lesson we kind of learned, even, I mean, I mentioned about the millimeter wave has a lot of fluctuation. In midband, you also have fluctuation to some extent, right? So this is the earlier I show you actually using kind of carrier aggregation, you can actually getting up to 2 gigabit per second bandwidth. But that's basically based on you have a lot of aggregation. If you have more mobility, if you, for example, vehicle drive around, you don't always have all the channel available, right? So this is actually show you because of you have that problem, your bandwidth also fluctuate, even though not at the magnitude as the millimeter wave, right? So again, you pose the question, how do I actually design application to make application 5G aware to know that, hey, you may actually lose one channel, your bandwidth is going to drop dramatically. What should you do, right? So those are the part we also kind of let us design, apply machine learning to design kind of throughput prediction algorithm, first for the millimeter wave, later for the carrier aggregation side. Right. So anyway, so this kind of basically summarize what we have learned, especially pertinent to the remote driving we're going to talk about. Right. So one of the kind of key part is that I have emphasized the 5G, you can achieve really high throughput, but that's mostly happen in the downlink side, right? So if you look at the downlink, this is only just a mid-band, you can achieve at least 1.5 gigabit per second. But if you look at uplink, those part of the scale is a 10 times difference, right? So we actually barely, I mean, peak one is some cases would exceed 150 megabits per second, right? So it's almost 10 times less. If you look at average is going to be at least 5 times less. So the average here, you're only getting less than like this one's AT&T less than 50 megabit per second. T-Mobile is the best around 70 megabit per second on average, and Verizon also around 70, right? So that compare that to the average uplink, I mean, downlink throughput is hugely less. The same thing also happened on the latency part, right? So latency also uplink is worse than the downlink. So you have this uplink downlink symmetry, right? But on the other hand, many applications, this will show you the latency part, right? So the latency going to be at least twice higher on the uplink compared to downlink. But many applications actually so many applications actually require a lot of uplink, right? So this is where give us a good segue to talk about autonomous driving. Autonomous driving, for example, you need a lot of data when you do the teleoperation. You need more data from the uplink than downlink. So let me just quickly go over autonomous driving. So my interest in autonomous driving was actually separate from the 5G wireless network. We started looking at autonomous driving, tried to say how we can actually leverage autonomous driving to kind of design kind of service to help the users. We had an NSF Smart Connected Community project in 2018. So we're looking at, and partially doing that project, I realized at that time, autonomous vehicle is not there yet. So it's difficult kind of try to tell people how we can use AV for solving societal problem without actually making the autonomous vehicle works, right? So even though we had the project for several years and the autonomous vehicle still had a lot of problems. So that's where kind of led me to combine autonomous driving with the 5G, because as I was reading about the 5G, one of the use cases of 5G is the so-called remote driving, or in the 3GPP or the 5G AA, which is 5G Automotive Association, which is organization try to looking at the 5G support for autonomous vehicle. They basically using a term called teleoperated driving, TOD. So we all know today now situation has changed dramatically. Now robot taxi has been deployed in many cities, right? So actually robot taxi, Waymo just started to testing in Minneapolis, right? So So we have autonomous robot taxi already deployed in many cities. Waymo had like up to 10 places now that deploy robot taxi service, mostly in the southern and western part of the U.S. where the weather is much nicer. So, but on the other hand, even the robot taxis, it's working fine in many situations, but there are always situations robot taxi do not work yet, right? So this is the case. For example, there's just, if you pay attention to last year, there's several kind of news article talking about problem with Waymo, right? So for example, there's a LA person missed his flight because the robot taxi couldn't figure out how to get out of the parking lot, so getting stuck. So anyway, so those are kind of problems. So we had the I'm gonna skip this slide, right? So we at the time we were kind of working on our breaking low latency project. In September 2024, actually, New York Times had an article talk about and the role of teleoperation, right? So I had an article called "When Self-Driving Cars Don't Actually Drive Themselves, That's Human Come to Rescue, Human Actually Try to Help," right? So that's a kind of show you we still need some human intervention, right? So human intervention can be in the form of driving, but could be in the form monitoring assistant, right? So this is actually way more just this is actually an article just published a couple months ago, and maybe actually just the past months. I'd say way more executive admit actually they have teleoperator in Philippines to monitor and help the robot taxi, even though the teleoperator don't actually drive. They had to essentially, for example, changing the routes or do some update or help the vehicle to, for example, if you get stuck with the parking lot because we more doesn't know where's the exit, right? The human had to say, hey, this is the exit, go out from here, right? So this is the need. The human had to see what's going on, right? So which means you need the information coming. The same thing that Tesla also said the need using both the human driver and the remote driver to help. So anyway, so we have been kind of working on remote driving since at least 2023. We started in 2021, 22. We had the NSF size large project that Hongwei kind of alluded to earlier. So we have been kind of working on that project for a long time. And the university actually bought a level 3 research vehicle, which is a Chrysler. So we have been, for this NSF project, we actually make that the remote drivable. This is just show you have a little toy kind of wheel. We can control the vehicle. So we have a kind of, besides kind of just make it remote drivable, we're actually building a remote driving pipeline. So essentially for sensor data, getting data from the vehicle, from the camera, multiple cameras, send it over teleoperation station. So this is show you example of the teleoperation station we have, and then sending the remote control, command and control back to the vehicle to control it. And so we have been building such a pipeline that's already kind of working. So I can show you 2 minutes of video showing our driving test. So the student is sitting inside our lab. We have our postdoc there as a human, just a human operator, just in case there's something happens, so can take over for safety reasons, because we are not allowed to have a car without human. So this is actually testing our parking lot. And this is actually looking at in the construction zone. So that's where we kind of control.
So there's a good trust between the postdoc and the driver in the
Yeah.
room, right? That's awesome.
So this is some of the testing we have done. Right? Yeah. So that's the kind of what we have done, right? So just give you the taste, and you look like okay, everything's it seems working fine, right? So why do we need to do more research? Actually, when one of the students I asked, new PhD student were asking, he said, "Oh, we're making it fun. What's the new research problem we need to really working on, right?" So in fact, actually today. And just last year, I mean, there's several startup on the AV teleoperation, and one in the Europe called the Raid was bought by Grab, the kind of food delivery, the Grab Hub, whatever the one in Singapore, and the US. There's a couple of company also are doing that. Right? So as a researcher, we want to understand, does the 5G network actually able to support the remote driving, right? So we want to do it from a more rigorous point of view. So anyway, so given the kind of time we have, I'm gonna quickly just go over it, right? So we know that we basically the question we ask are the 5G network up to the task for teleoperation, right? So we show some demo, it seems to work, right? But those are the situation which is much kind of controlled environment. If you had to really do that in a normal environment, especially you want to help autonomous vehicle when they have a problem, right? To human to take over, we need to kind of understand what today's 5G network can do and where it actually fall short, right? So we can improve the network. So one of the kind of key part already kind of alluded to that the autonomous vehicle actually has a lot of sensor on it, right? So you have LiDAR, camera, etc. For remote driving, we need some of the sensor data send it to a teleoperator. Then teleoperator is going to send a command. So there's actually a huge amount of bandwidth that need for the uplink, right? So the uplink actually need, if you think about just sending a single camera, it's going to be less than 10 megabits per second. But if you have multiple cameras, so our vehicle has like total 5 or 6 camera, right? If you try to stream all 6 camera, you may not have sufficient bandwidth. On the other hand, the downlink one with sending control commands actually require very little bandwidth. So this is actually very different than traditional cellular network designed for, right? Which is a downlink heavy, the uplink actually is very light. In terms of latency part, the uplink bandwidth based on the human reaction, right? So this is based on the 5GA requirement. We need a kind of glass to glass from the camera to the teleoperator screen. We need 100 megabit per second. Right? So downlink even shorter one, but we know that downlink actually reasonably well. So my slides actually do self-driving, switching the slides for me, which you probably want me to finish up the talk very quickly. So anyway, so I mentioned we have building this pipeline.
So actually, Zhang, just to clarify, I think if you have time, I think we don't have to rush. You know, we can complete however you have planned originally.
Okay. Right. So for kind of understand what the 5G is up to the task, we actually conduct a lot of measurement studies. So using both our MinCAV autonomous vehicle, but also we rent a fleet from the university, putting on the camera LiDAR because it's much easier, especially just if we just want to do some experiment, not actually control the vehicle and stand 5G. So also equip another vehicle with camera LiDAR so we can do a lot of measurement. Partially because for the MinCAV vehicle, we had to pay money it's expensive to use that for experiment. Right. Let me see. Yeah, so this is kind of just show you one sample round we have done. So we have the basically do driving. So this is a onboard vehicle talk about the LiDAR information. This is actually the end-to-end measurement in terms of the frame, each individual frame, what the time what the latency. You can see this. In this case, this is the early result. We have not optimized it. So the other if you look at many of the end-to-end latency is beyond 100 milliseconds. So this is partially because also the wire network, we are not optimized that side. Just okay, yeah. So this is another kind of example where we were driving near the university and also downtown. And I show you the latency performance. So so now let's looking at what kind of results, what we have learned from all this measurement study, right? So one kind of key kind of insight, this is actually a lot of the teleoperation, AV teleoperation startup company that often do, they actually may just using one single camera. So in a single camera, because you just need up to 8 megabit per second, we know the 5G today actually even uplink able to support that one. So that's actually another problem in terms of just the general bandwidth. So we did a study, for example, using the V8, V9, just a different compression, V8 equivalent to H.264, V9 equivalent to H.265. Both V8 and V9s are open source. The codecs that we can actually study. So you can show, for example, if you just look at the network-to-network latency, we have 99.9% we can actually deliver the frame within 100 milliseconds. Right? But if you stream multiple, in this case, 3 cameras, we then facing some problem. At least 10% of the frame going to require more than 100 milliseconds to deliver. Right? So that's potentially can cause some problem. Right? So the problem actually lies, if the channel is good, it's actually fine. The problem is when the channel become bad, right? Especially during the high mobility. So here we actually quantify how does the latency changes as the channel condition changes. So we're using channel CQI, the channel quality indicator reported by the UE as an indicator. When the CQI is high, right? So which basically means channel is good, we can have like 400, this is 0.4 frame to frame delay. And when the channel conditions is worse, right? The average performance is almost double, right? And this is partially because when you have channels bad, you also tend to have higher so-called the error rate, the block level error rate, right? So here we show you how the errors in the transmission, this is in the MAC layer and physical layer, impact on the frame delay, etc. So essentially, the challenge is that if the channel condition is good, we probably work fine. But when the channel condition are good, especially during high mobility, you're going to have more retransmission. Right? Retransmission in the physical layer, MAC layer, also lead to higher latency, right? So how we can do. Okay. And the worst problem, in fact, actually is the handover, right? So when you're actually driving, you're going to hand over from one base station to another base station, right? So as you drive, you have to kind of hand over from one to other. So that's involve some control procedure. So that's actually has a lot more, having more problems. So here, this is kind of show you as a one trace, and this is kind of orange dots indicate the handover point. You can see the throughput kind of fluctuate because of handover. So handovers is unavoidable when you're driving because unless you're driving in a circle around some area, right? So otherwise you have to hand over between one base station to another base station. And there's a lot of this part is due to the control latency. You had to kind of hand over from one base station to another. There's a lot of procedure you had to follow, right? So corresponding to the handover, you actually can see this is again, ignore all the everything else. So this is basically look at the latency, frame latency. You can see the spike one is actually all due to the handover, and not. So this is basically during the handover where you tend to have a channel getting bad for one. That's why the reason you actually hand over to a different base station. Right? So that's kind of the problem on that causing for remote driving. Right? And the worst cases is actually you had a situation, not just a handover, you also had something called the ping pong handover, which you have observed from our measurement study. So this ping pong handover, basically using this as an example. So this is where you can see you will connect to this base station. So this is like the different color indicate different base station. So I need to somehow my stuff self-driving. And you hand over to this blue one, but then coming back, right? So you have this ping pong handover. So sorry, the slides moving by itself, right? So this is the case you have the ping pong handover. You hand to something for another base station very quick for a short time, then hand over back, right? So you ping pong. This is situation more generally you have unnecessary handover, right? Hand over a green one, then back to the pink one again, and then back to the white one, right? So ideally, you don't want to avoid to hand over to the green one, then hand back to the pink one. You want to directly go to the white one, right? So this, because each handover procedure introduces a lot of latency, and you have this kind of handover, you're going to have a on kind of ping pong handover, unnecessary handover, going to introduce additional delay. So I show you kind of one video we have, and pay attention to about a two second as this particular timing interval, you're going to see there's a video frozen. So this is, we have a 3 screen. Let me put it again. You see the frame stop, froze, and then go. Right? So this will show you the handover problem, and this is due to the kind of ping pong handover. Right? So in this particular situation, there's no other car and no other events happening. It's okay, right? So, but if you have some kind of critical event, teleoperator may react much slower. Right? So this kind of give you a much more detailed view to show on the impact of handover on the latency performance. So this is a kind of latency spike due to handover. So in particular, you have ping pong handover going to have a much more worse impact. Right? Okay, so in summary, what we have learned through the measurement using teleoperation as a specific vertical cases, right? So one, we already mentioned this downlink uplink asymmetry, right? So for many emerging application teleoperation, we need more uplink bandwidth, but today's 5G network is designed opposite, right? So you have more bandwidth on the downlink, but very little bandwidth on the uplink. Right? And second part, we talk about the channel condition, variable channel condition, especially on the high vehicle mobility, going to cause some problem. Right? And lastly, but most importantly, is the frequent handover introduce latency. Right? So we need to address that problem. So now maybe just quickly kind of talk about our NSF break and load project. So this is the project based on the insight we have learned, try to kind of address the problem I just highlighted. In particular, try to address the problem of the frequent handover, right? So to see what we can do to solve that problem. So this is the project we just getting started last fall, and this is it's the TIP program, right? So it's not a fundamental research. We had to do demonstrations. So we have need to do demonstration at the end of second year. So this is basically the title of the project. Right? So the goal is basically try to tackle the challenge I just talked about, how to ensure we have a safe remote driving and do pilot demos. And kind of university involved besides University of Minnesota, we have Utah, and UC Riverside, have two industrial companies, the General Motors and the Nokia. So this is the co-PI here. So let me just give you kind of high level idea what this project is about. Right? So again, we are still working on it, so we don't have complete solution. So just want to give you some basic idea, right? So the idea is we want to make the 5G or next network vertical aware, and to in particular address the handover problem, right? So the basic idea is basically say you have vehicle, you're gonna, for example, you're gonna turn here. so you have, for example, 4 base station around the intersection. We actually can use the information to say, hey, I'm going to turn around here, so maybe I should hand over from this one to this one, not to the other two, right? So we want to be able to inform the network, this is our trajectory, and then tell me, using that information to decide which base station to hand over instead of just based on the signal strength. Right? So basically say, hey, now the base station say, we're going to ignore the other part and try to hand over. So that's kind of basically the idea we want to look at. Right? So then can tell the base station to prepare to hand over, etc. Right? So that's the kind of basic idea. We can actually do the handover, so we can also optimize the process, right? Set up the time, the kind of data path ahead of time instead of just wait until the base station already attached to the target base station, then to change in the control plan or the core network data plan, right? So this is the kind of basic idea. And the second part is we also can, based on the vehicle mobility, to do adaptive link adaptation instead of using just the same MCS. For example, we're actually using mobility to and say if a vehicle travel faster, channel can be bad, we may actually using a lower MCS instead of high standard MCS. So that's kind of basic idea, right? So the question, how do I actually do that, right? So the key part, we are trying to utilize the capabilities by the Open RAN capability, which allow us to potentially control the 5G cellular network, right? But the O-RAN by itself is not sufficient because O-RAN was designed mostly for operators to optimize their own network, not for vertical awareness, right? So one of the things we need to do as part of the project also enhance the O-RAN to make that vertical aware so that we can map, for example, trajectory application information to the network, and also using the network can provide information to the vertical application. For example, I know I have to have a handover. I may actually do video adaptation differently. So that's the kind of basic idea what our breaking node project is about, right? So we're basically taking a phased approach. We first at the coming up in the summer, we had to mostly solving the ping pong handover problem, and then the phase 2 and year 2, we're also going to incorporate some of the cooperative driving features, some other kind of using kind of predictive resource allocation to help the application to make decisions. So there's 2 phases that we're hoping we'll get this thing done. So anyway, so that's basically what this project's about. I'm going to jump to the concluding remarks. I think we have good timing, so I think we should be able to finish by 12:30. And I want to kind of summarize on what we have learned, right? So we know that 5G was officially rolled out in 2019. I mean, I got into 5G research, mostly try to leverage 5G to help design kind of interesting applications, right? So the question, now that we are 6 years into 2020s, has 5G delivered on the promise, right? So based on what I discussed, you probably can guess 5G has not, right? So in fact, actually, there's many news articles talk about 5G has been a disappointment. So starting like 2022, 2023, just a few years after 5G was deployed, a lot of people complain 5G is disappointing. So this is an article actually just published, I mean, updated in this month, March, talking about 5G sucks and even worse than 4G in some ways, right? So partially again, because you have this high fluctuation, actually making the application look kind of perform worse than 4G, which is much more stable, right? So now we are almost at the time we're going to talk about 6G, right? So maybe we should forget about 5G and directly jump to the 6G, right? So in fact, actually this week, you guys probably know that the Mobile World Congress is happening in Barcelona, right? So Qualcomm, actually, this is an article just fresh off the rail on Monday or maybe in the weekend, talk about 6G. So talk about the 6G, right? So the question is, what is 6G is about? There's a consortium to look at the 6G, right? So of course, the 6G is going to be about AI. I think everyone is talking about AI, right? So now the question is, can AI really solving the problem of 5G, right? So anyway, so kind of stepping back. Personally, I believe, right? So the reason I'm looking at 5G and also looking at autonomous system, I know the future autonomous system going to be play a huge role in the society, right? So we already see a robot taxi, autonomous vehicle, and the robots are coming, right? So those are the kind of autonomous system. We already have drone, many other type of drone that we can have advanced kind of air mobility. And I believe all the things wireless network, especially 5G and 6G, are actually going to be critical, right? So all the system rely networks, is particular wireless network, right? So especially using some of the foundational model that can only be run in the backend cloud or even on the edge, can't be run on the autonomous system themselves because you don't have enough battery, whatever. So which is kind of important for us, right? So 5G, the wireless network, I'm telling my students, everyone want to do AI, but I say, wireless is still important. Think about how you combine the two. So anyway, so this is kind of my vision, right? So what the 6G can happen, right? So if you look at the autonomous system, we're going to have digital twin, we're going to have real network, right? So and the autonomous system going to running in the autonomous system going to sense, and that data need to send it to, say, building a digital twin to make real-time decision. So how we connect those things, we need a network, right? So, and also human supervision is important. I still firmly believe human always going to be, if not in the loop, always going to be on the loop, right? So that's where 6G or next G going to be hugely important. But the question is, how do we actually solving the problem of 5G and then move us to the 6G, right? So we're going to use AI, machine learning, but the question is 6G really is just AI plus 5G plus AI? Is that the 6G, right? So, and how can we actually leverage the AI for solving the problem we have? So instead of just fall for the hype or the buzzword, right? So that's pretty much conclude what I have today, right? So the work I talk about a contribution from many of my students, master's degree student, undergrad student, and also postdoc, and also have quite a number of collaborators, including Hongwei, we kind of started working on together. So any questions?
Yeah, great. Thanks a lot, Zhini. Okay, so thanks. We still have many people with us. Actually, thanks for hanging around. Any questions from I guess the folks online? You can actually raise your hand or post through chat. So this is a very exciting talk, actually very exciting work. So while other folks may be preparing their question, maybe I can get a few started. Let me start with a very simple one, actually. You mentioned the uplink throughput, right?
Right.
And latency. I'm curious, based on your study so far, of course, we know the TDMA frame structure matters, right? Besides that, are there other major factors that's contributing to the longer uplink latency?
Right. So the
Or
one
throughput, yeah.
fundamentally
Yeah.
is the whole architecture, cellular architecture is asymmetric, right? So the base station is the one control everything. For uplink,
Yeah.
at least for the standard kind of service, uplink, the UE always had to request, sending a schedule request
Yeah.
and receive, waiting for the grant before you can transmit, right?
Yeah.
Right. So that's one. I mean, in the URLLC, they're supposed to try to solve the problem by pre-grant, right? So essentially, but again, the question, if you don't know when do you need the resources, you still have to always do request, right? So that's one of the fundamental limitation. The second part is the UE, the power is limited, right? So your transmission power is always lower.
Yeah.
Your channel condition is always not as good as the downlink.
Yeah. Right. Okay, so we have a question from Aziz. Was there any difference in the handover process disruptions in a standalone 5G versus non-standalone architectures?
That's actually an excellent question. So here, when I talk about teleoperation, we're actually using the T-Mobile only, which has the 5G standalone service. If you have the non-standalone, the problem even worse because you had a handover. Because in the non-standalone cases, you had a handover from 4G to 5G to 4G, 4G then to 5G, right? So you actually involve a lot more handovers happening. So the latency even worse.
I see. Good. That's a good question. Right. So I guess another question I have was about this teleoperation, right? I guess that's for the size large project.
Right.
Just any particular reason you use Chrysler? I guess in order to get that experimental platform set up, do you need actual Chrysler to provide any special support, or you don't actually need it?
No, I mean the vehicle we have is so basically the vehicle we bought. I mean, I didn't buy we convinced university to buy as a research vehicle, and so that one was bought around 2022, I think. And basically, you have a company called Data Speed. They basically you had to having a special device called a drive-by-wire system putting on top of the vehicle to make that vehicle more drivable. So one of the they have both the Ford vehicle and the Stellantis vehicles that actually they do, but it doesn't work for GM vehicle because GM has a lot of security stuff they don't want you to remote drive. So that's actually one problem we have with the braking law. The GM had to try to figure out how to make the vehicle remote drivable.
I see. Okay, I
This
see.
have a lot to do with the Data Speed equipment, how
Right.
they actually work with the vehicle.
Right. I can't forget the name for that. Basically, there's something you plug into the CAN bus, right? Then you can
Right. So it's
mount,
a drive-by-wire system that
Yeah.
has to be
Okay.
that accept the essentially for example, control command to control some of the lower layer system.
Right. Okay. Any other comments, questions? I think a lot of these questions are quite exciting to explore. I think even how to enable this vertical aware application and no vertical how you call it vertical app aware,
Right, the
vertical
vertical
aware
aware
networking, right?
Yeah.
There's of course algorithmic issue, but also the architectural question, right? How that can transform this. Awesome. I guess, Zheng, how's your availability? If you have a few minutes, we do have a small room set up. We
Sure,
can
I can.
quickly,
Yeah.
while we're here, because otherwise maybe difficult to find the time to get together again.
Right.
We can
So
just briefly
should
chat
I
over there then.
join the post-webinar meeting? So should I?
Yes.
Okay.
Yeah. Hopefully
Okay,
we'll not have this problem again.
Right. Thank you for everyone. Sorry for the glitches. I should have tested. I didn't realize it's a WebEx. Otherwise, I thought it's a Zoom because we had a meeting on Zoom on Team.
Yeah, sir, we are still old-fashioned.
But
Thanks again,
lucky.
Zheng, for the wonderful talk.
Yeah.
Yeah.
Bye.
All right. See you around.
See you. Yeah.
Thanks, everyone.